The Greek pre-Socratic philosopher Zeno, pre-Socratic means all the philosophers before Socrates. It's a whole class of Greek philosophy. Zeno believed you could not leave the room. You could not walk out of a room. Zeno was a student of Parmenides who, like, for example, many Hindus, believe everything that you see is an illusion and nothing is actually real, and there's like a transcendent reality that you're not seeing, and everything that you think you see is an illusion, right? Zeno wanted to support Parmenides' point of view with some mathematical logical arguments. So he said, for example, it's impossible to leave the room because to walk from your seat to the door, first you have to walk halfway from your seat to the door. And then you have to walk half of the remaining distance, which is 1/4. And then you have to walk half of that remaining distance, which is 1/8. So we say, just to simplify things, say it's 1 meter to the door. All right. First you have to walk a half meter, then you have to walk a 1/4 meter, then you have to walk an 1/8 meter, you walk a 16th meter, and this process, of course, can subdivide forever. So as Zeno said, since the distance from your seat to the door is composed of an infinite sum of finite quantities, that distance must actually be infinite. Therefore, you cannot actually leave the room. All right, now we know from calculus that Zeno's error was that he didn't really understand how the infinitely small interacts with the infinitely large. And that's what limits and infinite series gave us, in the world of Leibniz and Newton and Dedekind and a lot of other people who studied that. And so what we say about it now is, actually, you can leave the room because actually you can keep adding these up, but geometrically you can see that they add up to 1 meter. So the problem isn't that this cannot possibly add up to 1, therefore everything you know is wrong. The problem is this does in fact add up to 1, therefore the mysterious thing that's going on in these 3 dots requires some more thought. All right, so we now have some tools to give that some thought, because in fact this sequence 1/2, 1/4, 1/8, etc., that is a geometric sequence. In fact, it is the sequence 1/2 to the n. All right, it's geometric, and a sub 1 equals 1/2, and r equals 1/2. And so we can say things like that about it. So for example, we can say that the nth term, the nth partial sum, so if I add up finitely many of these, I have a nice formula for what we get, which is a sub 1 times 1 minus r to the n. We developed this last time over 1 minus r. We developed it last time and we summarized it on this nifty sheet, and it's right there. All right? That's the nth partial sum for a geometric sequence. Okay, all right, fine. So, but that's only finitely many terms, and our problem is we want to deal with infinitely many terms. But well, let's start with, for this particular sequence, we can say that s sub n equals our a sub 1, which is 1/2, times 1 minus 1/2 to the n, because that's our r, over 1 minus 1/2. All right, so this is 1/2, this is 1/2, they cancel, and I really have 1 minus 1/2 to the nth power. That's what s sub n is. All right, so what we're going to say, in order to say, so we can justify that this equals 1 because you can leave the room. If it didn't equal, if this added up to infinity, then Zeno would be right and you wouldn't be able to leave the room, which it might sometimes feel like you can't leave the room, but actually you can. There just might be consequences that you're not willing to face. Anyway, what we do to handle the infinitely many, like what is the ... here, that was Zeno's problem. Zeno didn't have this tool, the limit as n approaches infinity of s sub n, all right, would equal the limit as n approaches infinity of this quantity, 1 minus 1/2 to the nth power. Well, let's put that in brackets maybe. All right, and now we can do the same thing we did with improper integrals. The limit as n approaches infinity of 1 is just 1, so we really only have this limit. So we have 1 minus the limit as n approaches infinity of 1/2 to the nth power. And then this is a geometric sequence with an absolute value of r less than 1. So this is geometric with absolute value of r less than 1. As we discussed last time, that limit is 0. This part of the limit is 0. So this part right here is geometric with absolute value r less than 1. Therefore, the limit is 0. So that equals 1 minus 0 equals 1. And we see that that infinite sum is 1 as we expected. So that gives us some nifty things to talk about. So this limit as n approaches infinity of s sub n, we think of this as, this means that you're adding up all infinitely many terms. And we're going to see lots more justifications of why this actually works. And it isn't really a contradiction at all. It's just what goes on in here is what's counterintuitive. All right, what goes on in the world is actually very intuitive and it makes sense. What's going on in here is not so obvious, and that's why we need calculus to analyze it so that it accords with our real experience of actually being able to leave rooms. So what we call this limit as n approaches infinity of s sub n, we call it the sum from n equals 1 to infinity of this a sub n. So sum as from n equals 1 to infinity of a sub n is what we mean by that is the limit as n approaches infinity of the sum from. Now I need another variable because I'm now using n for my upper limit. So I'm going to call this k equals 1 to n of a sub k, right? So it means I'm going to sum up a finite number of them, and I'm going to let that number of finite terms that I find increase to infinity. N is the number of terms I'm finding. All right, so that's also the limit as n approaches infinity of s sub n. Yeah, so in particular, we can say that the sum from n equals 1 to infinity of 1/2 to the n, which is our sequence that we analyzed here, is equal to 1. And if you don't believe me, certainly you'll believe a TI calculator, right? They never lie. I'm really just showing off my calculator at this point. So I'm going to show you we can do this. If I can figure out how to work it. That's the problem with these nice calculators. Here, let me clear that, show you where it came from, just for kicks. All right, so if I go menu, calculus, you can do sums on the TI-84, but you can't do sum to infinity. So we're going to do sum of n equals 1. We're going to put in, let's see, parentheses, fraction, 1 over 2 to the power of n. And then we'll have our, if I can get to my upper limit on this thing, limities. There we go. And so I can just, we got an infinity key on here. It's kind of nifty. Hey, look, it's 1. All right, and TIs don't lie, except under certain circumstances. And then the trick is to know when that is. All right, there you go. So that's an infinite sum right there. This is what we're going to be talking about for a long time. This is your first, just an infinite sum, a sum of infinitely many things. I mean, the integral is really an infinite sum as well. So it's not that new, but we're going to sort of looking at different kinds of sums now. All right, so yeah, we're going to look at some different ones next.